Okay. So does this look about right? Okay, so I want to pick up where we left off. So we left off talking about isotopes and radioactivity. And so we kind of sketched out sort of the instability, the way an unstable atom, as it starts to get really large, starts to naturally shed particles. And then when it does so, it releases energy in the form of radioactivity. And that's kind of something we have. So there's naturally occurring isotopes in nature that are radioactive. And like uranium, for instance, we all know that, plutonium, we all know those as sort of being bomb material. But they're actually natural. So it's not like if some scary country with intent to do harm to everybody who actually seems to be somewhat peaceful and pacifist, if you will, if there is such a thing. If they have a lot of uranium in their country, just because they're mining uranium doesn't necessarily mean that they're going to be able to do anything with it, right? Because one of the things is naturally occurring radioactive isotopes aren't usually in great enough abundance nor great enough purity to really cause a problem, right? Which is the reason why we don't necessarily freak out if somebody is mining radioactive materials, because we know that they have to have technology and industry to be able to purify it and to enrich it, right? So it's kind of like you have to sort of concentrate it and get it to a point where it's actually usable for particular purposes, right? So most elements are dirty, if you will. So that is to say they're ore. So they're mixed in with rock and things like that. You can't use that for anything useful. That's the reason why you've got enriching programs and things like that to kind of get your uranium away from the ore and purified in a concentration to where you can actually do something. This is the reason why in sort of nuclear speak, right, you have this idea called weapons grade materials. And what that basically means is that you have managed to not just harvest the radioactive ore, but you've also managed to purify it and to concentrate it into high enough levels to where now you can actually blow cities up with it, or you can make a bomb with it, right? So you're not going to hurt anybody if you just throw like a uranium ore rock at them. That's not going, nobody's going to be impressed with that. So you have a lot of work to do, right? This is one of the reasons why it took so long for us to develop the first atomic bomb, was because that was what the whole Manhattan Project was about, was trying to figure out, basically how to get your uranium to a certain level to where you can actually make it go boom. Is that a question? Yeah, so glow in the dark watches. So no, you don't use uranium, and actually your glow in the dark stuff is different. This is a different stuff now. But yeah, that is true. That glow in the dark watches back in the day, especially. I mean, I'm thinking like back in the 60s and 70s. This is when we used to go back. They used to use radioactive isotopes with reckless abandon. And so what made your watch glow in the dark was this little isotope that was on there, and it was irradiating. It was causing all sorts of problems and things like that. So they have since backed away from the scarier isotopes. Now, are they still using isotopes? Probably, but they're probably using something that is a little bit less powerful. So you're probably talking about, a fairly insignificant radiation source. Because the idea is radiation is everywhere. there's radiation. So it's not like, most of nature is non-radioactive and we're safe. And then you have a few of these elements out there that just kind of try to restabilize themselves, and they're emitting all this radiation all throughout the universe. It's like a constant. As a matter of fact, you're bathed in radiation right now. When you go outside, you're bathed in radiation. So the universe has radiation interwoven into it everywhere. And it's just it's just kind of part of the universe. And so when you're looking at like a radioactive source, like in the case of an exposure issue, you're always looking at not necessarily like, is there some sort of a radioactive thing on my watch making glow in the dark, as much as you're saying, well, is that actually more than what I would get just walking outside? And so before, it was more than you were getting just walking outside. So they were basically radiating. But now what they do is they take a less powerful isotope, bring it down to less than general exposure. And then the idea there is the same, because the idea is like, well, you're actually getting less exposure from your watch than you are just actually walking outside, right? So that's your background radiation. And that's always a presence. So it's always happening everywhere. So let's take a look then at radioactivity, and let's kind of put this kind of to work for us, shall we? So we have a couple of things that we can do. Some of you guys, obviously, in terms of putting things to work for us, that's one potential way of putting it to work for us, right? We can make our watches glow in the dark. But you don't need radioactivity to make your watch glow in the dark. I mean, we do have, digital watches that you can illuminate in the dark. So you can do other things with it. You don't need to have things glowing in the dark. So that's not necessary. A little bit more important is, in terms of an application, is nuclear medicine, right? Has anybody ever had like a nuclear medicine test, or a loved one? Either a stress test, or like maybe you've had to take a radioactive tracer for like maybe thyroid detection or something like that, right? So that's nuclear medicine. So that's a beneficial version of it. And generally speaking, when you're doing some sort of a test like that, what you're essentially doing is you're feeding yourself this radioactive isotope. So it's decaying, and this energy is kind of being released, but it's really low level. Right. So like, for instance, my background is cardiology, and we used to do nuclear stress tests all the time. So we'd always have to inject the tracer in there, the isotope. And of course, patients would be like, okay, wait a minute, you're doing what? Right. This sounds like, deep state 1950s, Chernobyl type of stuff going on here. Right. So no. It's basically that the equivalent energetically to like 2 chest x-rays. That's basically what it is. So it's like really low level for the most part. But the cameras that are looking at that and looking at the energy that's being put off by these tracers are very sensitive. So they can see it. You can't, but they can see it. And that's all you need, is for those cameras to be able to see it. And they can create really nice pictures. Like a nuclear stress test is an actual, if you want to know whether or not you're getting good blood supply to your heart, that's the one you need to do. Okay. And cardiologists know it. And that's the reason why a lot of cardiologists want you to go straight to that one. Yeah. Do what? An angiogram. So an angiogram is more like x-rays. So it's kind of more like an x-ray version of it. So it's a descendant of that. Whereas this one, it's more like an actual isotope that you take, and then it goes somewhere. Like, for instance, in the thyroid situation, it's an isotope of iodine, which only has one place to live in the body, and that's in your thyroid. And that's the reason why we use iodine tracer, is because it doesn't go anywhere else. In the case of the nuclear stress test, it's just a general tracer that we inject into your bloodstream. Because the idea is, what we want to do is we want to take a picture of your heart and see where your blood is, or is not in the case, right? So if you have a clogged artery in your heart, then there's going to be a section of your heart that's going to be dark. And then the cardiologist will know, it's like, well, I know where that is. That's, the left coronary is going to be feeding that area. So we need to get you down to the cath lab and get you a stent. Right. Yeah, typically speaking, it's usually easier to reach, because angiograms, if you take a look at the reality of things, insurances are only going to pay for certain things. They want to pay for the least possible that they can pay for. And that's not a knock on them. They're trying to manage costs. And they realize that some doctors are gougers. But, you know, there is a progression. Like, for instance, if you can't see something on a nuclear stress test, then the next level would be getting down to the cath lab to do like a diagnostic cath, or an angiography or something like that, where they're going to actually get in there with the angiogram or something like that, and they're actually going to start threading through your arteries to actually measure things in there. So you can do a cath, but that's invasive because they're going to have to cut open your femoral, which is always problematic because that's a major artery. You can bleed out on that one. So they have to be careful on that one. They have to thread it through your femoral up to your heart. And so it's not a pleasant thing. I don't know. That sounds very scary, but I don't know exactly how they get in there. Yeah. So, so it depends on where it is. Their entry point, a general diagnostic cath is going to the femoral. And the reason why you do that is because cardiologists like that one. So if you're going to the wrist, you're only working, you know where it is. So you just basically go in the shortest route. That's what's happening there. The problem with your arm is all those arteries are pretty tiny. And they're harder to work with. There's a femoral is much bigger and all of that, but it's going to connect to your aorta, which is also an important area. So cardiologists are, they like, well, wait a minute, if we're doing a diagnostic cath, we're going to check down all of your big arteries, these killers. This is where if you clog these guys up, it's sweet. It just, it's gone, right? It's like you're over, right? So it's I was trying to say too sweet, which is what one of our cardiologists always said, which basically means now, basically. But that's, so they want to get in there to see, that's kind of how they do it to get to those major arteries. So depending on where you have the clog, obviously, you would have different access points. And we're getting good technically where we can do that. That's an example of radioactivity at work. Now, what about radioactivity? It's a problem. I mean, aside from the idea of a nuclear bomb dropping on us, that's obviously a problem. Or Fukushima, right, where a tsunami compromises the integrity and the security of our nuclear power plant, or Chernobyl, which is a previous generation, a full-on meltdown where you pretty much annihilate an entire city, an entire area of a country, make it unlivable. So aside from that, what are some other negatives? Well, let's get a little closer to home. You think you're safe? Oh, you naive Coloradans, you. You're not. What's our problem? Uranium? No. Plutonium? No. Well, microwaves everywhere, right? What's our problem? Does anybody have a radon mitigator on their house? Big old set of white pipes. Have you seen them on houses? Big old set of white pipes going up the side of the house, almost looks like a chimney stack made out of PVC, right? It's not even pretty. It's pretty unsightly. If you ever see that, look, pay attention to houses you go by. That's a radon mitigator. Why do you need a radon mitigator? Because radon, which is a radioactive element and a gas, is a natural component of Colorado soils. And so we have a lot of radon in our soils. Generally speaking, it's not a problem. You're probably walking on radon as you walk back and forth through campus, but it's not a problem because it's a gas. And so as that radioactivity comes out in the gas, it naturally dissipates into the atmosphere, and so it's not a problem. But if you happen to have a basement with an open crawl space in your basement, it is a problem. Because what will happen is that radioactive gas naturally emits from the soils, from your crawl space, and accumulates in your basement. And so for those of you who have a finished basement with a crawl space, and you don't have a radon mitigator, oh, foolish souls. You better get a radon mitigator, because over time it increases your frequency of lung cancer, because there's nowhere for that gas to go. So every time you go down into the man cave to watch the Chiefs unfortunately win again. Yeah, so as a Raider fan, that's the one thing I have in common with the Broncos fans. It is very enjoyable to watch the Chiefs lose. So that's the one thing we can find common ground on. Of course, everybody wants to see the Raiders lose, but right now it'd be nice to see the Eagles just destroy the Chiefs. And I'm not an Eagles fan. I hate Philly, but basically what happens is, if you test, and you can get these tests actually at like Lowe's or Home Depot, stick it in your basement. It'll tell you if you're above normal. And if you are, then basically they're saying, you need to get a radon mitigating system. Basically all it is just a fan. They just cover the crawl space, and it's a fan that's always on. It's never off. It just sucks the radon gas. And they kind of cover it with like a tarp, that they kind of pin down, and they've got the ventilation system on there. It just basically sucks the gas off of the soil and then emits it into the atmosphere. So it's not accumulating in your basement and causing you harm.
What if you just have a crawl space?
But no basement? If the crawl space is open to the outside atmosphere, you're fine. I mean, if it's like, if you have access to it, like if the gas has a way to get into your house, it will. If you're worried about it, the radon tests at Home Depot are actually not that expensive. So, and it's worth it because, if you get a house and you realize you're in a market like this where your house is extremely valuable, but so is everybody else's. So that means you can sell your house and then go nowhere. And you realize you're going to be staying in your house for a little while, it's worth it, right? Because you don't want lung cancer, right? That's just not something you want. Okay, so that's naturally occurring, but so there's a lot of natural radioactive isotopes out there. But what I wanted to do is I wanted to circle back around and sort of complete the thought that we left on this slide. Yes, we didn't talk about half-life, did we? But I want to now. I'm ready, right? So when we take a look at isotopes, what we have basically is a rate of decay, right? So that is to say these atoms, which are really, really large and unstable, start to shed these particles and thereby release their energy in the form of radioactivity, but they do so at a predictable and a constant rate, right? Now, the example that I want to give you of how this works out is with carbon, right? Because we've already been introduced to carbon, yes? Carbon has 3 different isotopes, and we know the carbon-14 decays. So when we take a look at carbon dating, basically what carbon dating is it's trying to determine the age of something by looking at this very sort of predictable process of radioactive decay. Now, here's the thing. All the carbon in your body is basically made up of carbon, but all 3, carbon 12, 13, and 14, because that is just a naturally occurring source. That's just what happens in nature, right? So you don't get to pick and choose. You just get what you get. So in you, if we were to analyze the amount of carbon 12 versus 13 versus 14, the ratios of that carbon inside you would reflect the same ratios that you see in nature. So like, for instance, the plants that you eat, like if you're a fan of spinach, like I am, then the carbon ratios of 12, 13, and 14 in the spinach are exactly the same as they are in me. As a matter of fact, my carbon 14 is decaying. So it's disappearing. As you're alive, it is decaying and it's disappearing. However, the reason why you don't see a disparity or a disappearance of carbon 14 is because you keep replenishing it. So every single time you eat something, you're basically sort of refilling your carbon 14 that you've lost. So as long as you're alive and eating, you're constantly replenishing your carbon source and you're maintaining your natural carbon 12 to carbon 14 ratios. Now, the second you die, you are no longer replenishing your carbon, but your carbon 14 continues to decay at a very predictable rate. So then what that means is your carbon 12 to carbon 14 ratio changes, right? As carbon 14 sort of decays into nitrogen, remember we talked about that one before, then what that means is your carbon 14 is disappearing and your carbon 12-14 ratio starts to change over time. So what we can do is, like if you've been dead for a while, is we can measure your carbon 12-14 ratios in you versus what's in the environment. The difference we should be able to predict, and we should extrapolate it back in terms of the number of years. This is exactly what we're doing, especially like in archaeology with carbon-14. Like for instance, when we sort of discovered the ice mummy, and the ice mummy had some sort of a cool textile on them or something like that, right? We're going to say, when was the person last alive? Well, we take a little bit of that textile, we do some carbon-14 dating on it, measure the 12 to 14 ratios. They're going to be different than what's now. But the difference is then will allow us to extrapolate back in time and say, oh, well, this mummy shows a pattern that's consistent with their carbon-14 having been decaying for about 3,000 years. So this person lived 3,000 years ago, right? That's when they stopped. That's how carbon dating works. Now, how does this tie into half-life? Well, the idea of half-life is simply the amount of time it takes for half the sample, that's the, not them, to decay. So for instance, for carbon, your half-life is about 5,700 years or so. And so generally speaking, when you take a look at a half-life decay, you can see you've got maybe, here's the amount of sample that you have over here versus time. And so you kind of have a curve that looks something like this, where at about 50% of your sample, this is what's called your T1 half, or your half-life. So that time frame is the time at which it takes for half of your sample to decay. But notice, you still have more to go, yes? So that's just kind of like a little marker for us to kind of figure that out. For carbon, for instance, that's 5,700. So generally speaking, this is really good for us because 5,700 years ago is like well within, in a very robust way, well within recorded human history, which is the reason why we use a lot of carbon dating for archaeology and things like that, because it covers the human history span quite nicely. However, would you use carbon-14 to age rocks? No. Why? Because, you know, if you're talking about something that potentially could have been made 1 billion years ago, you're done. There's no carbon around, right? Even just a few million years ago. As a matter of fact, probably the safest limit for carbon to use is to 30,000 years, maybe. That's pushing it, actually. I'd probably keep it under 10 if I were, because the further you go, the less accurate it gets, right? So if you're in that sweet spot of carbon dating, it's robust, but the further you push it, the less accurate it gets. Now, that's some limitations on that, right? So what about other things like plutonium, right? We mentioned plutonium, we mentioned uranium. So these guys have a different half-life. As a matter of fact, plutonium has a half-life of 26,000 years. Think about that for a second, right? A lot of times every now and then the country has this sort of energy discussion. You're like, okay, we need to get off fossil fuels. We need to get wind energy going and electricity and all that sort of stuff. And oftentimes one of the alternative energy strategies tossed in there is nuclear, right? And you hear that from time to time. But the question is, you know, how come we obviously know that there's a lot of power in nuclear, right? So why haven't we figured this one out? Why don't we have a whole bunch of Fukushimas powering a place like Tokyo, which it can? Good.
Isn't it because we don't have what to do with, like, hold on the energy, even though
So yes, a couple of things, right? Number one, it's hard to control the reaction because basically what's happening in a nuclear reaction, in a nuclear reactor, is a controlled explosion. That's basically what's happening. And what a meltdown is when you start to lose that control and it starts to go out of control. And then that's the reason why you could pretty much vaporize. That's the reason why we were worried about that has the capacity to basically do to Fukushima, do to Tokyo, because it's in Tokyo, exactly what happened to Hiroshima and Nagasaki, which is basically obliterated, where you would have tens and tens of millions of people dying. And that's the worst case scenario for a meltdown like that. That's the reason why everybody was like, there was like a moment of global, like, right, I mean, arrest there, because that could have been ugly quick. Luckily, the Japanese moved very quickly. I think for what happened, they did a great job of keeping that under control, because we still have Tokyo with us. So that's a good thing. But yeah, no, it's not that, right? So a lot of times, people will be like, well, why not? Because there's so much power, we'd be able to pretty much light Las Vegas indefinitely. I mean, it's like, we wouldn't worry about energy. And that's kind of what the pro-nuclear people talk about. But here's the problem, and you're spot on. It's not that's the problem. The problem is, once the fuel rods, which are usually mostly plutonium, once these fuel rods are no longer energetic enough to produce the energy that we need, they're still radioactive, right? And so they're no longer good for energy production, but they're still radioactive and they're still a problem. So the question is, what do you do with them? And that's the issue, right? We do bury them, but you can't bury them forever, right? Right now, what we do is we bury everything in Nevada under Yucca Mountain, poor Nevada, right? We do nothing good for Nevada. I mean, we bury our nuclear waste in there. We drop bombs on them. We hide our aliens there. So, I mean, Nevada's really kind of the armpit of the Union. We do treat it pretty horribly, actually. If I were in Nevada, I'd be a little myself. But hey, consolation prize, we give you Las Vegas, right? So that may or may not be a good thing, depending on how you see the world, right? But the idea is, if you're accumulating all this nuclear waste, guess what? That's going to be around for 26,000 years. Oh, wait, that's only half gone. So the other half is still around for another 26,000 years. Think about this for a second. This is going to require not just one generation to have a really good, sound nuclear waste management plan, multiple generations across thousands of years. So just the half-life of plutonium exceeds recorded human history. And when you think about it, we can't cooperate on anything in real time, even when our life depends on it. COVID is a good example, right? So we have nearly, and this is me being a very negative anti-humanist, to be able to manage nuclear waste over 26,000 years is a near impossibility. We are not that smart, right? We do not have what it takes to cooperate long enough to manage this waste for that long a period of time. We can't even, I guarantee we can't even do it for like 2 decades without arguing. As soon as the new generation comes, and a new generation of that, and new generation of that, it's going to be out the window. Yeah. Not that I know of. I mean, theoretically speaking, you could always use it for weapons. I mean, if you just want to kill people, you could drop a bunch of radioactive plutonium in the middle of their city and then just like Chernobylize everybody. It's like, hey, look, we win. Really? Where are you going to live? Genius, right? This is what humans do, right? We are not smart enough to pull something like this off. And that's just blunt truth. Okay, we've shown zero capacity to pull something like this off. Zero. Even in our best, most noble moments, we've never even approached the kinds of levels of cooperation and cohesion that would be required to handle something like this over this span of time. Think about this. 26,000 years. Oh, no. 52,000 years, because we're only halfway there in 26,000. Yeah. No.
Think about Jesus, he was only 2,000 years ago.
Yeah, right. So when you look at major historical things, and then think about also just how much of a shift in society has happened in just 2,000 years. Right? I mean, yeah. Even so, that basically means if the Romans figured out how to deal with plutonium, we would have long since screwed it up multiple times. During the Dark Ages, we would have screwed that one up. During the Renaissance, we would have screwed that one up. I mean, just about every single century, we would have screwed all this up. So we have no capacity whatsoever to deal with this. So what do? The only thing we can, we buried it in Nevada. So go to Yucca Mountain.
How deep did they bury it?
Pretty deep. I mean, it's like literally under the mountain. I mean, it's deep. It's deep in there, and it's super, super secure. Like you can't approach. This is like most of Nevada. It's like one of those things. Like, yeah, you want to walk in there? We're just going to shoot you. Yeah, welcome to America. We're going to shoot you. We don't really care what kind of a democracy we are. You cross into my yard, and I will shoot you dead. I don't care who you are, voter or non-voter. You know, nobody cares, right? When it comes down to it, every country's the same. They're all largely dictatorial. Wow. How's that for a piece of cynicism? That one, very dark today, I'm feeling. It's gonna be a long day of darkness for me, apparently. But anyway. Oh yeah, they've like dug a big old, it's kind of like NORAD, you know, where they basically just kind of build a big complex into the mountain. So it's kind of that same idea.
Wherever the president's gone?
Yeah, that's the reason why Colorado Springs is probably one of the top 3 shots for a nuclear attack.
They say that they have functional McDonald's down there, but they just have like a McDonald's employee, like in the secret bunker.
In NORAD?
Yeah.
Oh, they got to have something. I mean, you're potentially talking about bunkering in there for an indefinite period of time. So,
like a guy, or does he like work there year round?
I would assume it's.
but see, nobody really knows, right? Because all that is super, super top classified. So nobody gets to know even where NORAD is. We know it's there somewhere, but nobody really knows where it is. Yeah. No, and who's in charge of that is the Department of Defense. So you don't get anything out of Department of Defense. It's the politicians that squeal. Like even the president doesn't even know anything about what's going on in NORAD because the Department of Defense is in charge of it. Because if we need to go to NORAD, the Department of Defense gets in charge. The president is largely just. Yeah, a lot of people think the president kind of has the keys to the kingdom. Actually, most presidents probably don't have as much access as you think. There's the deep, deep stuff. Yeah. Well, Cheney's like one of the overlords, but unless you're like one of the masters, right? One of the Sith lords in charge of all of this, for you Star Wars fans, right? You got to have a red saber to get in. So let's go ahead and take a look at the electron arrangement, right? So now this is kind of where we want to focus some of our attention on. And so we kind of talked a little bit about the Bohr model, but we want to take a look at sort of this sort of spatial arrangement, because we want to sort of flesh this out a bit as well. But a couple of things, first of all, that we kind of have sort of been teasing out, we want to kind of build it a little bit, and then we want to get to this one to really explain kind of how this is going, is when you take a look at electrons, the reason why we focus on electrons from pretty much here on out, this is pretty much our discussion, is because cells are essentially what's in the driving power behind chemical behavior. So when we're trying to build an organism and we're trying to build molecules to build that organism, then what we want to know is how do we actually build the molecule? Like what chemical behaviors do atoms have that allows us to be able to build that molecule? And that's what we want to know. Now, who's setting that chemical temperament, that chemical behavior? It's the electrons themselves, right? So from here on out, what we tend to do is we tend to focus pretty much like a laser beam on the electrons and what they can do for us in terms of building molecules so that we can build our organism. Now, the thing is when you take a look at different electrons, they're going to be whizzing around our electron cloud. That part we know. However, they're going to be living in like little neighborhoods called their orbitals. So generally speaking, when you take a look at electrons in the electron cloud, they're all sort of whizzing around in space, yes? However, not all electrons are the same. So different electrons will have different sort of energetic personalities to them. Some will be high in energy, some will be low in energy, but they're going to be whizzing around in three-dimensional space in that electron cloud. Now, is their movements random? Well, not necessarily, right? Because just like us, we move around the city. We can pretty much be found anywhere in the metro area, probably at any given point in time. However, are there areas where you're more likely going to be? Sure. How about the neighborhood you live in? You're more likely going to be found there, yes? For some of us, we don't really venture a whole lot outside of our neighborhood. So there's parts of the city we never go to, right? So being kind of from South Denver, you will probably almost never see me in the northern metro area. Almost never. Because I have everything I need. And so text of the city, which is kind of like the electron cloud, have these sort of defined these different neighborhoods within which we spend most of our existence. And on the level of the electron, those little neighborhoods are referred to as orbitals. Now, what we try to do in the Bohr model is we try to diagram out the different energetic profiles of these electrons. And that's what we're trying to do with the Bohr model. When in reality, spatially, they're basically going to be in that little orbital area that's sort of defining them inside their electron cloud. Now, one of the things that you need to really pin down in this particular discussion is one basic idea, definitional idea that comes to us from particle physics, that basically says that when we take a look at in which an electron resides, there can only be 2 electrons. That's it. That's your max. If you have more, guess what? You need to create another orbital. Okay. So that is one thing that sort of constrains this entire organization. So now let's go ahead and take a look at this. And what I want to do is I want to sort of take a look at the Bohr version. And then, of course, the spatial version. So this is the way it really is on the right-hand side. This is the way we diagram it out. Now, electrons themselves will have various energy levels. And the energy levels will increase. But we typically refer to these as energy shells. So for instance, in the Bohr model, each little orbit, they letter them here like K, L, and so forth. I tend to number them, okay? So each little ring is what's called a shell. And within that shell, you have a certain number of orbits. Different shells have different number of orbits. So here's what I want to do. I want to do a little bit of an exercise. I want to do it with sodium. And I don't know if anybody has a periodic table close to them. I know Bella had one last time. Yeah. Got to scooch over a bit, like over here. Oh, there we go. So let's start. What I want to do is I want to do an example with sodium. I'm going to draw the sodium nucleus. How many protons does sodium have? 11. I hear quite whisper. How many electrons does it have? Should be 11 if it's neutral. If it's on the periodic table, that's the assumption we make, right? So it has 11 electrons. Now, we have 11 electrons to deal with, yes? So let's go ahead and start diagramming them out in the Bohr model. The first thing we need to do is open up a shell. So we open up our first ring, our first shell, and we're going to call that one n equals 1. Okay. Now, in n equals 1, you have 1 orbit. That means you have a max capacity of 2 electrons. So what is that orbit? So the orbital that's in that first level is a spherical orbital, and we call it 1s. 1 for the first level, S for its shape, spherical, right? So basically what that means is these two electrons are found in this little orbital neighborhood somewhere. Okay. Now, let's go ahead and put those two electrons in there. Boom. Are we done? Have left. Yeah, so what do? We open up another shell. So let's open up another shell. This is going to be n equals 2. Now, from here on out, you have a max capacity for 8 electrons. Why? Because you have more orbitals in this second shell going forward. So let's take a look at the second shell. So now we have shell number 2. So here you can see we've opened up another shell and we've dropped in some electrons. So I'm going to basically put 1, 2, 3, 4, 5, 6, 7, 8. So there's my 8. I filled up that shell. Now let's take a look at this. What are the orbitals in the second shell? Well, the second shell also has a spherical one. So that's 2s, right? But notice that sphere is a little bit bigger than 1s. It also has 3 p orbitals. So 2 for the second shell, p. So 2p means you've got p orbitals in the second shell. But you have 3 of them. So the p orbitals are like a little mini cloud, if you will, that's shaped like peanuts. And it basically forms along the 3 axes of all the 3 dimensions, x, y, and z. So for instance, here is one along the x-axis, one along the y-axis, one along the z-axis. Now, remember our definition. How many electrons per orbital? 2. So how many electrons can I put in this z orbital over here? So how many go in this far right orbital? 2. Yep. How many go in the middle orbital? 2. How many in the left orbital? How many in the spherical orbital? Right? Because there's 2 for each orbital. How many electrons do I have now? I filled them all up, right? All my orbitals are full. I'm done. How many do I have? Yep. It's the reason why from here on out, all of your shells have a max of 8. If I were to open up another one, so what I take a look at sodium, am I done with sodium yet? What do I have left? How many electrons have I counted for so far? Yeah. So what do I need to do now? Yeah, open up another shell, right? No choice. So we're going to have to open up n equals 3. How many orbitals do you think n equals 3 has? Just like n equals 2, it's got 4, right? Because it's got a max of 8. So it's got a 3s and 3 versions of the 3p, right? The x, y, and the z of 3p. So it's got a 3rd layer of this. So you have another 8. So we stick our lone little electron out there. Am I done now? Yeah, that's it. All right. So what did we do? We took sodium and all we did was just diagram out our electrons, starting from one shell to the next, to the next, to the next, until we account for all of our electrons. And we've successfully built out a Bohr model for sodium. Now, when you take all these orbitals together, then what's going to happen is they're kind of all going to all cluster together and they're going to form this kind of like big gamish here, where you can see you've got your 2 s orbitals that are kind of in there. You've got all your p orbitals that are kind of in there. As a matter of fact, the more p orbitals you add in there, then the more spherical this whole thing looks on the outside. Okay. And then that's basically what your cloud starts to look like. So within a cloud itself, you've got all these different orbitals in there. Neighborhoods, if you will, within which these electrons, 2 electrons that is, will basically be hanging out. Okay. That makes sense? That's quantum mechanics, by the way. That's orbital theory is what you learn in quantum mechanics when you go through chemistry. It tends to make your brain hurt for a little while, but then it kind of starts making sense in some strange, weird way. But for us, it helps us to sort of do a couple of things. Number one, to understand the spatial arrangement of electrons in space, their actual physical position. And number two, for us to diagram out the personality of the electrons. And so here's one thing that I want to mention, just one more comment that I want to mention in terms of the actual spatial representation or its placement in space. So as you have all these electrons that are in these little orbitals zipping around three-dimensionally, they're going to be moving around in this large cloud, right? But one of the things is, as these electrons come together, because remember, the nucleus is positively charged, yes? A lot of protons in there. The electrons are negatively charged. So what's keeping the electrons from just crashing down into the protons, right? Because the positive and negative are attractive to each other. So what keeps them from crashing into the protons? Well, themselves, actually. In this particular case, we have lots of electrons. If we were all a bunch of electrons together, then since we're all negatively charged, we're repelling each other, right? So if we get too close to each other, we kind of do the whole personal space thing. Now, if we're all converging on the same thing, right, like a nucleus, like a proton, then the attractiveness of the positive charge is going to pull us in. But then at some point, we're going to start to feel each other's presence. And that repulsion between each other is going to be stronger than our attraction to the nucleus. So we're going to say like, whoa, we can't get any closer because we're getting too close. So what we're going to do is we're going to stay right about here, and we're just going to have nice, safe distance. And we're going to balance each other out. Okay. So we can get close, but no closer because we still have that repulsion thing to deal with. And so that in chemistry is a theory that we call the Vesper theory. So it's basically where the electrons sort of manage and balance themselves in space to maximize the attraction, but to minimize the repulsion. So it's kind of like a little bit of sweet spot in there. From flying apart? Yeah, that's one of the strong forces of the universe that we really don't understand very well. That's a nuclear force. And we know it's a really strong force. Why? Because when you split that atom, you annihilate entire cities, right? So we know it's a very strong force. Not really quite sure how that works exactly. But that is something that is a mystery. The other one is also a variation of that is like for hydrogen, for instance, it has one electron, one proton, is what keeps the hydrogen, because it doesn't have anybody to repel against, what keeps a hydrogen electron from crashing into the proton. Don't know that one either. At least I don't. Maybe particle physics physicists have a better explanation for that one. But that's probably related to that same idea of the nuclear force. There's just certain things you can do. And by the way, that's a thing. That's what makes quantum mechanics so difficult, right? It's because when you start to get into the world of quantum mechanics, all the rules that you used to know and understand all kind of get suspended, and it like just turns upside down. It's like walking into a Salvador Dali painting, right? Where everything just kind of seems a little surreal and it doesn't really make a lot of sense, and it's not very predictive, which is one of the reasons why astrophysicists have such a problem with quantum mechanics, because it doesn't seem like the universe can be run on quantum mechanics while at the same time show all the elements of relativity, because the two are like oil and water, and that's burned up many careers, including Einstein's, right? And we don't understand why somehow it just sort of shifts into this sort of crazy, wacky world of quantum mechanics at some small level. It's actually quite fascinating. But that's basically what it looks like. So the reason why I say that is because you add all those particular ideas in there, and then what you get is this sort of spatial, physical location of an electron. Now, the thing is, not all electrons are the same. What the Bohr model says basically is that electrons have different energetic personalities. As a matter of fact, what that also says is that, for instance, if I were a first shell electron, and you were like a third shell electron, from the Bohr model, we should never cross each other's paths, right? Just like the Earth never crosses the orbital pathway of Saturn, right? They just doesn't happen. We're straight. But the reason why we know it doesn't work is because if I'm a first shell and you're a third shell, we actually physically in space at times can be like right next to each other, which shouldn't happen, right? He may be going that way, I may be going that way, so we'll kind of like cross each other's paths. But here's two very different electrons, right? Very different personalities, very different realities, but in physical space, we're right here next to each other, right? That's how we knew the Bohr model was not right, because it's not that way. And not only that, but electrons have very different energetic properties. And so what we do in the Bohr model is we strive to sort of organize and characterize these electrons according to their energetic personalities. And so when we take a look at this, we have this idea of characterizing their energetic personalities versus characterizing their actual physical spatial arrangements, right? So those are two different activities. One requires a Bohr model, one utilizes the spatial model, right? That's kind of what we're doing. So let's take a look at some of the energetics. So in this particular case, we have an atom. So down here, we have our nucleus. And then we have our different rings. So here they kind of they letter them. That's kind of what they do in quantum mechanics, KLMN. But I've always found that to be abstract and confusing. Now, in a quantitative science, why would you add verbal labels, right? So your verbal intelligence is at war with your numerical intelligence. Why would you do that to somebody that's just sick and twisted? So what I tend to do is this is going to be the first shell, the second shell, the third shell, and the fourth shell. And of course, we've already gone through the number of electrons that exists at each one of these shells. Now, the important thing about each one of these shells is that they are not the same in terms of energy. So for instance, in the first shell, this is going to be the lowest energy shell. The highest energy shell is going to be the outermost shell, or in this case, the fourth one. And then of course, it's an increasing step of energy as you go up to the fourth. Now, what that does then is that basically means that the first shell electrons are going to be lower in energy than the fourth shell. So when we kind of do our little thought experiment here, where I'm shell number 1 and he's shell number 4, even though physically in space we're right next to each other, energetically, personality wise, I'm lower energy and he's higher energy. So our realities and what we can and can't do are completely different. It just happens to be we're right next to each other. Okay. Now, the important thing about understanding this is because what this does for us then is this also creates a situation that we've noticed where we have the ability to change this a little bit. So an electron that basically is in low energy, like a shell 1 energy, can basically begin at a very low energy level. All right, so I'm going to put this here, the very low energy level. This is an electron 1. Now, if we take an energy source like UV radiation, yeah. So, wait a minute. So, rephrase your question. So you're saying. Yeah, like a balance of energies. It's not that easy. And not only that, but remember when we start thinking of rings, it's easy to start thinking of rings, right? We say like, oh, well, you're kind of in the inner ring, so you're closer to the nucleus. So maybe you got a stronger pull and that's going to make you lower energy or whatever. But remember, these aren't in rings, where these guys are whizzing around in their orbitals. So this is their personality. This is like who they are, regardless of how close they are to the nucleus. So like, for instance, a first shell electron can be either close to the nucleus or further away. Now, in terms of balance of energies, generally speaking, it sounded like you were talking about an outside energy source balancing the internal energy source to make sure that everything kind of stays in harmony with itself. No, it's not really that way. Because then what would happen is every atom would be beholden to an external energy source, and we don't see that. What we see is each atom is kind of like a complete unit. It's like an independent kind of event, if you will, not necessarily needing anything external, which means that an atom has everything it needs internally to stabilize its structure. Now, what that means, we don't know. That gets into particle physics, and how this all sort of goes together and things of that nature, right? So one of the things we can do, so if we take, say, for instance, a low energy level electron, so it's on like the first ring, one of the things we can do is we can take like UV radiation. So we can take some energy and we can beam this at our electrons. Now, as it turns out, these electrons can actually absorb energy. So this little low energy electron will absorb this UV radiation and it'll absorb a bunch of energy. And when it does, it's going to jump up to a higher energy level. And we, at this point, we give it an asterisk. That basically means that this is an excited electron. So at this point now you've got a decision to make, right? So you've got all this energy now in you. You've just sort of absorbed all this energy. So the question is, what are you going to do with it? Well, there's a couple of options. Number one, you could do nothing, right? That is to say you absorbed it, so just let it go. And a lot of times you do that. So if you were to just let this go, then the electron itself would drop right back down to its stable state, its lowest energy state. But as it does so, it's going to shed that excess energy it absorbed into a photon of light. This is the process of fluorescence. So anybody enjoy like playing around with the black lights around Halloween time? That's always fun, right? You get the fluorescent paint, you kind of paint stuff up and make it all kind of creepy looking and kind of cool looking, and you put the black light out there and it's all glowing and everything, right? Is that a question? Yeah, bioluminescence is a more of a general category. Fluorescence is an actual specific chemical version of bioluminescence.
You can find it a lot in geology.
Huh?
You can find it a lot in geology.
Yeah, there's like, you can actually see fluorescing minerals as well. You have to put a black light on it. So it is the thing. But basically it's the same basic idea, right? So when you take a look at that fluorescent paint that you use during Halloween to paint up your pumpkins or do whatever you want with it, right? What's happening is the electrons in the paint are actually absorbing the UV radiation. Those electrons are then getting excited. So they're jumping up to a higher energy level. And then once they're there, then they fall right back down. And then as they do so, they emit a photon of light, usually in the color of the paint that you painted, right? And so when you look at a fluorescent paint that's glowing under black light, it's like, oh, hey, look, that looks like light. It's glowing. Well, it is light, because what you're actually seeing is a photon of light. And so that is a property of this ability for electrons to absorb energy and then to release energy.
Would this be how modern non-uranium glow-in-the-dark watches work?
Yes, fluorescence is a much more natural process. And generally speaking, like probably most glow-in-the-dark stuff where you have to put a light on it and sort of shine a flashlight on it or something like that to get it to glow is probably this. So they took some sort of a paint that has a slight little bit of fluorescent capacity to it. When you shine the light on it, the energy of the light is being absorbed by the electrons, and then it's jumping up. And then when it's falling back down, it releases that glow. Okay. So it's the same basic idea. But, you know, that's kind of cool, but not really useful, is it? I mean, if you're an organism and for you, fluorescence is like your survival strategy, like you said, the bioluminescence thing, right? Where it's like, well, maybe if I fluoresce a bright fluorescent pink, then maybe that'll tell predators, don't eat me because I'm dangerous, I'll kill you, right? So that might be a thing. But still, that's just cool, right? I mean, it's not really useful per se. There's other ways you can do that, right? By the way, you don't have to be fluorescent to tell a predator that you'll kill them. They're quite familiar with, I mean, they've probably tried to eat you a few times. They know better by this time. So what can you do? Well, you've got it, right? So why not put it to work? Alternative number 2 is capture the energy. You've got it. You've just absorbed that energy in your electron. Don't let it go. Capture it, right? Capture it so that you can now put it to work for you and get some sort of biological benefit out of it. This isn't necessarily, this capturing concept isn't necessarily all that different from charging your cell phone, right? I mean, you've got energy coming through the outlet, yes? It's right there. You can either let it go or you can capture it, plug into it, and charge up your phone. What's happening is you've got some sort of a device inside your cell phone called a battery, whose job it is to basically capture or hang on to that energy that's just passing you by, right? And then what does it do? Then it uses that energy to power all of the apps and things like that on your phone. So that's a perfect example of, instead of just letting the electricity go by, capture it and put it to work for you, in this case, in your cell phone. So this is a really important concept, because if you're able to capture energy, what was one of the primary biological questions of life we ran into in chapter 1? Let's rattle some off. What were some of the big biological questions of life? What did we cover? Yeah, and that one was at the bottom, wasn't it? Everything was built on that. So you would imagine then, early on, one of the earliest discussions you have to have as an organism that you're trying to build is, okay, we want to do this, but we need to build an energy plan, right? We have some questions. Well, this right here, the capacity to capture energy and put it to work for you, is an enormous innovation in helping you to establish an energetic foundation. Think about it. You want to be able to have your cell phone turn on so you can use the app. What do you need? You need an energy plan, don't you? What do you have? You have one. You've got a battery in your phone, something to capture energy with. Now what do you need? A source of energy to capture, right? How many of you guys are energy scrounges? You're constantly looking for an outlet everywhere you go. Can I plug in? Like, yeah, we're right. How many, are you there? You look for those public charging stations and you're like, don't do that, by the way, unless you want to download a virus. They can hack into them and load viruses. So always bring your own charger, and just find an outlet that's just pure electricity. So yeah. So topic shift, but not as big a topic shift as you think, right? Because what are we talking about right now? We're talking about energy, yes? And that's our big energy plan. Well, here's the thing. We have a couple of chapters, part of the take-home situation, right? So that are going to be covering the whole idea of generating energy, right? So we have the energetics chapters, we have cellular respiration, with photosynthesis. All of those are associated with your energy plan. Now, the reason why we move into redox is because these guys are a type of chemical reaction that you see in chemistry that essentially drive energetic metabolism. So like when you take a look at the reactions of cellular respiration, when you're dealing with energy, you're literally trying to capture energy and you're trying to create an energetic molecule that you can utilize. These are the energetic metabolic reactions, and these are redox reactions, which basically stands for reductive oxidation. That's what this stands for. And this is a specific type of chemical reaction in which electrons are basically passed. So they're transferred from one molecule to another, similar to just like a relay system. So here's kind of what it looks like. It's Allie, since I'm sitting next to you, I'm going to pick on you. So in this particular case, like when we're sort of passing something on, I have a pair of electrons here, right? So what I'm going to do is I'm going to pass these guys on. Now, as soon as I do that, I have lost electrons, yes? And she has gained them. Now, if she passes it on, now she has lost and she has gained. And if they keep passing it on, then she has lost and she has gained. Well, if you keep doing that around the room, there's always one thing that's always true. Somebody's always losing electrons, somebody's always gaining electrons, okay? So that's basically what oxidation reduction is. Matter of fact, so when you take a look at this loss of electrons, that process we refer to as oxidation. If you gain the electrons, then we're talking about reduction. And so the way that I remember this is with a little memory trigger. Leo the lion goes grr. So loss of electrons is oxidation. Leo. gain of electrons is reduction. GER. As a matter of fact, it's very simple here, right? Because here you have two different molecules. Molecule A is clearly taking an electron. It's passing it on to molecule B. So this is the oxidation one. It's losing, right? It's LEOing. And then B is GERing, right? Because it's gaining the electrons. And so at this particular point, it is reduction. But now notice, you tend to go back and forth, don't you? Because when Allie passed, so when Allie first got the marker from me, she was reduction, right? She was gaining electrons. But then she turns right around and goes into oxidation. Well, guess what? If I have another marker to give her, she goes right back to reduction. When she gives it away, she goes right back to oxidation. So any given atom will oftentimes, like a pendulum, be swinging back and forth between grabbing, or excuse me, gaining electrons and losing electrons. So they're constantly oscillating back and forth between an oxidized state and a reduced state, because they're designed not to hang on to that electron, but to pass it on, right? And that's key. And here's the reason why. Because I want to take a look at a similar sort of a situation, only instead of a marker, I'm going to zip past Flower Day, and I'm going to go straight to St. Patrick's Day. Because I want to generate a pot of gold, like leprechaun style, like classic sort of leprechaun cartoonology, right? That's what I want to do. In this case, instead of passing on a marker, I want to pass on a pot of gold. And so it's kind of a nice little classic little pot, right? So lots of little gold coins in there. So there's a lot of stuff in there. So in this case, what this is like, pot of gold. So if I take this little pot of gold, then I will take my cuts, take out a couple, not all of it, don't get greedy. I'll need take a little bit of a cut, use it for what I need to. And then what I'll do is I'll pass those electrons on. So and then she'll take her cut, right? And then she'll pass it on. And then she'll take her cut and then she'll pass it on. So we're each kind of taking a little bit of money. Now, what are we using that for? We're using that to basically achieve some sort of a task. This is what's happening in metabolism, okay? Why? Because electrons are energetic. Remember, we just said that electrons have absorbed energy. That's kind of like an empty pot that gets filled with gold coins. And so what you do then is you start to put that energy to work. And so oftentimes, like if the four of us are like a team, let's say the four of us, our job is to figure out how to buy a Bentley, right? But it's not our Bentley. We're buying it for somebody else, okay? But that's kind of our job. So what do? We're like, well, we don't have the resources to buy the Bentley. So what do? We take our pot of gold. I'm going to take my cut. You take your cut. You take your cut. You take your cut. And with that money that I've got, it allows me to sort of pool our individual functions, because now we have and the four of us together can have resources to go and buy the Bentley. Of course, when we do that, we have no more energy. We have no more coin left. So we're right back to where we were, poor, right? But the Bentley now goes to whoever we bought it for, right? The president of the college, who's no doubt quite thankful that we just bought her a Bentley. But then where do we go? We go right back to where we started. A new pot of gold, taking our cut all the way down the line, and then we pool our resources to buy another Bentley. So we are in the process, Team Bentley, of pooling our resources from the energy that we're passing through and then buying the Bentley with that. Okay. That's how metabolism works. You're basically always taking a cut of that energy in the electrons, and as you're passing that through, that powers everybody's ability to sort of do their job, which ultimately is an energetic one, right? Because now, for instance, we have a new capacity driving the Bentley around that we didn't have before. And that's exactly what you're doing when you have something like this. That would be an example of putting a redox reaction, because we're passing that on between each other, to work in order to give us biological benefit. And who doesn't want a nice Bentley? In my 15-year-old Ford Escape, I'm one to talk. Okay, so let's take a look at the elements. Hmm?
It turns over on one of these things.
Yeah, right, I know. As long as it moves forward, stays intact, we're good. Okay, so let's take a look at the elements. So, if I can, just my body. So this, very colorful, is your periodic table of the elements, right? They're not all naturally occurring. The first 90 maybe-ish or so are naturally occurring. The rest of them largely are made in a lab, in CERN somewhere, so they're actually not real. And so obviously we're not interested in it. In physics you are, in chemistry you are, but we're not interested in those because they're not naturally occurring. We're interested in what we can use to build a biological organism, which means we're only interested in the naturally occurring isotopes, elements. And in addition to that, we're only interested in the ones that we basically can use to build biology. And so what would that be? So let's take a look first of all, before we get there, we'll get there here in a couple slides, but a couple of things we really need to do. This is a critical slide for us today. So if this was like, you know, you're trapped on a desert island and you only had one slide to take with you to remember biology with, this would be a good one to take. So when you take a look at the electrons that we have, we already established the fact that not all electrons are the same. Yes? We've already established that they have different energy levels. Yes? So there's only actually one type of electron. So not only are we only interested in electrons, but we're only interested in one type of electron. And that is what? The valence electrons. What are the valence electrons? These are the electrons of the outermost shell. All those others, don't care. So not even all the electrons are interesting to us. We're just interested in the ones in the outermost shell. Why? Because the valence electrons, more than any other, these are the ones that are determining, that's a, I guess, a shortened version of determining, just go with it. The chemical bonding behavior of an atom. So how you behave chemically is determined by your electrons, more specifically by your valence electrons. Okay. Now, these are the guys that are in the outermost level. So these are absolutely the ones we focus on, like, by a lot. Okay. As a matter of fact, because we're focused on the valence electrons, a lot of times what I'll do is I'll break down our designation of our Bohr model, instead of like the full ringed out Bohr model, into what's called an electron dot diagram. How many valence electrons did sodium have when we drew it out? One, right? So typically, because the valence electrons are the ones that are the biggest and the most important, we can abbreviate sodium with just one. Okay. What about chlorine? How many electrons does chlorine have?
17.
So let's go ahead and do its Bohr model. So there's 2, right? In the first one, we open up another 2. Now how many do we have? So we open up another one, yes. And then we put how many? There. So how many valence electrons does chlorine have? 7, right? So electron dot wise, we can draw chlorine as 1, 2, 3, 4, 5, 6, and then 7. Focusing, zeroing in like a laser beam on just the electrons that are involved in chemical bonding. Okay. Now, as it turns out, there are some that have a full shell. Yes.
Why is it obviously
You mean, why don't we refer to them just by their valence? We do. So like, for instance, if you were to take a look, so if you were to take a look at the periodic table, you've got group 1, group 2, and over here, group 3, 4, 5, 6, and 7. That basically is related, that's surveillance, right? Because group 1, where sodium is, that's group 1 because it has 1 valence electron. Group 2 is group 2 because it has 2 valence electrons. Yeah. So we group it. So, and that's we didn't group this, by the way, like that. Like say, oh, we want to put group 1 with 1 valence. What we did is we took the periodic table, organized it by atomic number, and the groupings just fell out that way. That's what I mean by periodicity. Like when we learn new chemical traits and it becomes periodic, it's like we didn't organize it that way. It's just by organizing it by atomic number, by its identity, it just sort of lays out that way in this sort of masterful pattern over and over and over again. With the valence, right? So you have group 1, group 2, group, I wonder if I can actually get the document camera up here. I probably can't. No. Return, please. That's not the one I want. Go back to the whiteboard camera. Camera control. Do a preset. Can you do a preset? No. 3. No, that's rear camera. Wait a minute. That. Okay. I don't know that I can. The whole system shows it. That's lovely. Lovely. Thank you. Thank you very much, CCD. Faulty technology. Let me guess. It's obliterated. Everything. Yes, it did. Thank you very much. Gotta repower. Okay, lovely. Okay, so this is it. So the other thing is that, like, when you take a look at the groupings, it also has a relationship to their ion, right? So like group 1 forms a +1 ion, group 2 forms a +2 ion, group 3 forms a +3 ion, and so forth, right? All the way, and that works out great. But then when you get to 4, it doesn't really form an ion, but like you start to get to 6 and 7, it's not a +6, it's like negative now, right? Because they shift from getting rid of to gaining in the middle here. Okay, so you can kind of do that predictive thing with the periodic table. I have to get this stuff. I'm not gonna, beggars can't be choosers here, so I can't expect flooded technology to work. Great, so I just destroyed everything. Oh, there it is. Okay. So the on group 8, which is the furthest to the right, these are what's referred to as the noble gases or the inerts, the inert gases. Why? Because as it turns out, there is a governing rule that governs your existence in all of the kind of the atomic temperament discussion. And that is basically this guy right here, the octet rule. What the octet rule basically states is that all atoms strive to achieve a full outer shell by bonding with other atoms or gaining and losing electrons. So for you, for an atom, this is like atomic nirvana. This is like your state of perfection. And not only that, but unlike sort of nirvana as we understand it, for the most part, we have quite a bit of satisfaction with where we are now, right? We just sort of come to peace with ourselves. There is no peace for an atom. So like right now where you guys are like, you know what, I'm not perfect, but I'm okay, right? I'm okay with that. No, that doesn't exist for an atom. To be imperfect is to be completely fractured, right? I mean, literally, like you cannot think about anything at all except what do I need to do to become perfect? It's all consuming fire that basically devours every atom, except the noble gases. Why? Because they already have a full shell, don't they? They've got 8 valence electrons out there. Well, helium has 2, but that's the inner shell, right? So everybody has 8 valence electrons, right? So helium has 2. What's the next one up from your periodic table? 10, which would be, right? And then 17, 18. Right? Because you're filling up the next shell, right? So you're going up by 8s now. So that's just basically running down the atomic numbers basically of the noble gases. Why? Because they're full in the outer shell. When you're full in the outer shell, you've achieved your octet rule. You've achieved perfection. The whole reason why an atom does any bonding at all with any other atom is only to achieve perfection. If you're already there, you need nothing. So you don't need to bond with anybody. This is the reason why they're inert. So they don't need to bond with anybody. They're already there. Everybody else is in a state of desperation, right? Everybody else is in a state of disrepair, desperate to try to become perfect. And that is an all-consuming fire of every atom, and every atom will not rest until they achieve perfection. How to do that? Complementation, right? Listen, I'm not perfect. You're not perfect. Why don't we join forces and cover each other's imperfections? And if you consider us as a pair, as a duo, then we've got ourselves covered. So we look kind of perfect, but only in the context of us as a pair. Okay, it's like a complementation strategy. So here's our periodic table of the elements. And so you see, you've got group 1, and then group 2, and then group 3, and then 4, 5, 6, 5, 6, 7. It's kind of weird the way they pull oxygen out there. And this is 8. So these guys are the ones that are perfect, right? So neon, do you find any molecules with neon in it? No. Neon doesn't bond with anybody. Argon, nope. Don't find that one either. Krypton, xenon, radon, nope. They don't bond with anybody. They don't need to. They're already there. They're already perfect. If they were to bond with somebody, they become imperfect. Why would they want to do that? Right? So they don't do anything. Not only that, but when you take a look at the periodic table, and I want you to take a look at this, is the closer you are to perfect, the crazier you are, the more desperate you are. So think of it like this. So who's perfect? Well, let's think about it. How close is chlorine in group 7? Very close. How many do they need? One more, right? So these guys are insane, right? They're really close. How close is sodium? Also pretty close, right? But in kind of a different way. What does sodium need to do? If it gains 1, it's going to be 2, right? So it could go 2 ways, right? If it gains, it has to gain how many to fill up its shell? 7, right? If it loses it, what does it need to do? Yeah, you lose 1, right? And then what happens? Close off that shell, right? You don't need it. It's empty now. And you fall back on the next one, which is full. So which one do you think is easier to do? Fall back, right? It's easier to get rid of 1 than to gain 7, right? That's going to be difficult, right? And with chlorine, it's the same thing. Chlorine could either what? Lose 7 or gain 1. Which one's easier? Gain 1. But they're really, really close, aren't they? Let's take a look at carbon. Carbon is 4. What does carbon need to do? Gain how many? 4, right? Or lose 4. It's right in the middle, isn't it? It's not going anywhere. Think about this. Let me explain to you how the psychosis works here and how these valence electrons determine the temperament of these atoms. Think of it in terms of a race. in a very desperate race, like something that's a very like Olympic, right? So something that you basically trained for your entire life. Your entire life has been dedicated to this whole pursuit. And you're kind of in this race now in the Olympics, and you're like really, really close to like achieving your dream, right? Think about this. To lose this race would be like so devastating because it would be like almost like an entire waste of an entire life. I mean, this is what you've done for a living, right? So it's been desperate. And imagine that you're like running and you're like almost at the finish line and you're like right there. I mean, you can like the tape is like right there. I mean, so close you can smell it, right? How desperate are you to cross that line at that point? Very desperate, especially when you look out of the corner of your eye and your arch nemesis is right here, nose to nose, right? So what are you going to do? If they're like literally like nose to nose, photo finish, what do you want to do? You get desperate, don't you? What are you going to do? Oh, better than that. Right? If I touch it with my tongue, I got it. No, better than that, because you're desperate now, right? This is an entire lifetime's worth of existence in this one moment. So what are you going to do? Wait a minute. I'm going to cut my tongue off. If I throw it over the line, I win. Technically speaking, as long as the tongue is still warm, that's still part of me, right? But I'll win. Is that desperate? I won't be able to talk anymore, which may be a good thing, right? But you win. That's pretty desperate, isn't it? Why? That's because you're so close. You're like just so close that it's like desperate. You can see this in sports all the time, right? When you see championship games in particular, right? You see like two teams that are very close together. I mean, they're so close. We just saw it with the Bengals and the Chiefs, didn't we? The teams were close. They were right there, 20-20. And the Chiefs were getting dangerous. And what did they do? That defensive end made a bad decision, right? A desperate decision that pretty much screwed the game up for them. Why? Because they were so close, right? That's the reason why he did it. Now, would there have been the same amount of desperation from that defensive end had it been like 23-0 at that particular point? No, because the game would have been over. They would have known that this is, I mean, we've lost. There's nothing we can do now. It's over. So you're not as desperate, are you? Are you still competitive? Sure. But are you going to injure yourself to make a play? No, it becomes a business decision at that point, right? To quote Deion Sanders. Right? You preserve your body so you go into the off season and reload and rest, right? And the same thing is true here. Somebody who's running this race, who's maybe middle of the pack, who's maybe running 8th place, are they as desperate as the guy ready to cut his tongue off and throw it over the finish line? No, why? Because they know they're not going to win. By the way, they also know they're not going to lose either. They're kind of somewhere in the middle. So for them, the psychology is completely different. They're like, you know what? I'm just so happy to be here. There's a lot of that in the Olympics, right? You know, I don't care what happens. I mean, I'm just happy to actually be here. I mean, it's just like so cool to actually be here. You know, if I place, even like if I'm able to really put some leg into it, this last stretch, maybe I might be able to get up to 6th, maybe even 5th if I really, really press hard. But, you know, I'm happy, you know, a place between 5th and 10th place, that's not bad. I mean, I'm running against the world's best. This is the Olympics, for crying out loud. And I'm somewhere in the middle of the pack. That ain't too shabby, right? That means I am basically in the top 10 of the world. So it's a different psychology. It's a different way of looking at it. So that person's not as desperate, are they? So they're not going to go cutting their tongue off or their arms or anything like that. But you can see their temperament is completely different. The same thing is true for the atoms. Because chlorine is so desperately close, it becomes desperate in its chemical personality. Same thing with sodium. Carbon, by the way, right in the middle, gain or lose, either way, I'm pretty chill. I'm pretty well balanced psychologically speaking, right? Which is one of the reasons why carbon is the major component of biological organisms, because it is an exceptionally stable atom. And it's a good one to build on because it is stable. Now, yes.
Why isn't iron like, I guess, perfect? Because aren't all of its levels full? Like, on the valence electrons?
Yeah, I mean, so, well, iron's one of the transitionals, right? So there's different versions of iron. There's either ferric or ferrous, or either an iron that takes on either a +2 or a +3. And so because it's transitional, those two different ions have very different behaviors. So they're a little bit less predictable than like the traditionals, like the group 1 through 7s. That's the reason why. But it is certainly, and the reason why it's pulled out is because it's a big deal in biology, especially in mammals itself. And that's what they're pulling out here. They're pulling out the atoms that have a lot of importance to them. I mean, it's slightly different. We'll see in the next slide just how important the others are. It's not like oxygen is the most important one. Well, it is. Try living without it, right? So that's a big one. But I mean, the idea here is there's different elements that are more important than others, and that's kind of what we have here. That's what we're talking about. So this has a particular lens on it that I'm just using as a general thing. They're actually trying to make a point with all these things pulled out that I'm not making. Because there's different ways to look at it, and they're all valid. It just depends on which facet of the diamond you're looking at. It's still a diamond, basically. So the idea here is that when you take a look at chlorine, remember this thing is desperate, right? It's desperate to get a hold of an electron. Sodium is desperate to get rid of an electron. And so a lot of times what I do is I like to anthropomorphize it a little bit. If you imagine chlorine, right, being super desperate, I mean, you're so close. I mean, you're just so close. I mean, you're just about ready to spontaneously get combust. You're about ready to jump out of your skin. You're just so close, right? I mean, have you ever been close to something, so close to something like that? I haven't. I'm carbon. I mean, that's just the way, that's my life right there. I'm carbon. And I'm just like, hey, give me 4, I'll give you 4, we're good, whatever. I don't have the temperament for a chlorine. I'm just not there. But here's the thing though, I always like to imagine chlorine is sort of like being this sort of atom that's sort of in this dark alley hiding behind a dumpster, waiting for some poor suspecting atom to walk by so it can jump on it and grab its electron and run. Right, that's what it doesn't really care what's happened there. It's like, oh, I'm sorry, you're dying because I just ripped out your jugular. That's okay, I need it, right? And this is mine, so you can go die now. So I don't really care, right? So that's how selfish you are. I mean, you want yours. That's what this octet rule does. It consumes you. It's an all-consuming fire. And so on the flip side of it, however, sodium is kind of like the opposite psychology, but still is aggressive. So oftentimes sodium is waiting for some poor unsuspecting atom to walk by. It's going to jump on him and it's going to be like, here, take my wallet. I don't want that money, right? So you're like confused now, right? So as an atom, you're like, wait a minute. So was I just mugged? Because you just gave me like $1,000. So I was like aggressively like philanthropized or something like that, right? It's like, I'm gonna give you this money, right? So it's like, so it's a little confusing, right? So, but that's kind of the way sodium is. It's like hot potato, right? It's like, here, take it. I'm out, right? I don't want anything to do with this. But it's equally aggressive. That's the reason why I want to make it aggressive like that. So, but
So that makes NaCl or like table salt that like they're soulmates because one really, really, really wants the wall,
Exactly.
the other one really, really,
Yep.
really wants to give up.
which is my exact next point, right? Because behind the same dumpster is chlorine sitting right next to sodium. So it's a chlorine, you want that electron, sodium, you want to get rid of it. You guys are a match made in heaven. Meet each other. Sodium's like, hey, you want mine? Take it. Right? So then what that means then is when sodium is in its happy place, it exists as an ion. Why? Because it lost an electron. So it tends to hang out as an ion, but only because chlorine, who gained one, also exists as an ion, chloride ion. Now notice they're both happy, aren't they? Chlorine is happy because it picked one up. Sodium is happy because it got rid of one. But that's only going to be true if they form this association with each other. The second they disassociate from each other, they are back to disrepair and back to psychosis. So the reason then why atoms bond with each other is to satisfy each other's octet rule. It's a complementation. I want to get rid of one. You want to take one. Let's form a truce. We can form an agreement over this, and then we will achieve each other's octet rule, but we will always be in association with each other. And as long as we are in association with each other through a bond, then we will satisfy each other's octet rule and we're happy. This is the reason why atoms come together to form bonds with each other to form molecules. Oh yeah, in biology, this is not, this is like one of those equilibrium things. We like to break equilibrium. So what we oftentimes do in biology is we're like, oh, this is nice that you guys formed this nice little association. Guess what I'm gonna do? I'm gonna tear it apart. And I'm gonna, it's like a bad reality TV show, right? It's like, I'm gonna tear you apart and then I'm gonna basically reassociate you with somebody else, right? This is kind of like what happened on The Real Love Boat. If you guys ever watched that, that's a really bad reality TV show. But that's what they did, you know, people hooking up and then you tear them apart, you add new people in there and so it's just, you're messing with people. It's like, this is kind of sick, but like what train wreck sort of a sick thing, right? You can't turn away because it's like, why would a normal person agree to do this to some other person? But anyway.
So are they gonna be like, because it's sodium and chlorine are, you know, they're trying to bond because they each have what the other needs. Like, are they gonna most likely bond with, like, I guess it comes into play. So would potassium and bromine also try to bond as much as possible? Because potassium needs to get rid of 2 and bromine only needs 2.
Yep.
Or would bromine go for 2 sodiums?
So yes, so matter of fact, so we had did sodium chloride, but potassium can go with fluorine, bromine, it can go with sulfur, it can go with oxygen. Calcium could go with chloride, calcium chloride, that's another salt, magnesium chloride, bromide, it could go with any of these.
I guess the better question is, I just completely said that wrong because I got columns and rows mixed up. Like, would oxygen prefer to go with what's B? That's a beryllium.
Mhm.
Or 2 sodiums.
The nice thing about chemical bonding is there is no preference. So oxygen, if beryllium's around, it's like, hey, beryllium oxide, let's do it. If magnesium's around, magnesium oxide, let's do it. It doesn't care. At the end of the day, the atoms don't care who they bond with, just as long as they bond with and they cover each other's octet deficiency. They're happy if they do that in general, right? I mean, getting deeper into that question is starting to move into the realm of chemistry and the different chemistry between all these different molecules and things like that. But for the most part, they don't care as long as they get their octet deficiency covered. Okay. So what we'll do is we'll start off with this slide next time.